Hello and welcome back to Everybody Codes 2025. Today we are working on a grid again, and we have a list of instructions that allow us to draw a very long wall. Each instruction tells us which direction the next part of the wall turns and how long that section is. The only possible directions are left and right turns, which means we're working on a square grid. So in our example, we start facing up, and then the first instruction tells us to turn right 90 degrees and then move to the right by 3 cells, which creates a wall of length 3. And then we just repeat this, so on and so forth. Okay. So our goal is to reach the last segment of the wall, and we can't go through the walls, of course. So for example, in this case, the answer is very straightforward. We just go straight down. In this somewhat more complicated example, we see that we might need to move away from the endpoint and wrap around walls. So the first part is a relatively straightforward pathfinding algorithm. We can just construct the grid and use breadth first search to search for the endpoint. As a quick reminder of how breadth first search works, if we imagine that we have a graph, this grid simply is a graph where all of the open cells are nodes that are connected to each adjacent cell, then in order to find our way from a given start position to a given end position, we start with a set of already seen nodes and a queue of open nodes to check, which both begin with just the start node. And then each time we take the next node off the queue and add all of its neighbors that have not yet been seen to both the seen set and the queue. So in this example, we first add this to the seen set and the queue, then we mark it off and add its neighbors to the seen set and the queue. When we process this one, its neighbors have both been seen already, so nothing new gets added. This one gets processed, and we see the end state, which means that we are done pathfinding. So that's how breadth first search works. So let's first grab our input. The first character tells us the direction we're turning, and the second direction tells us the length of the wall. Okay. So we can construct our grid as a map of coordinates to cells. And the reason I'm doing this rather than storing it in a 2D array is simply because it's a bit inconvenient to store in a 2D array when we would have to pre-compute the bounds of the array and then also account for some of the coordinates needing to be offset to avoid negative coordinates. Instead, if we set our start position to 0, then our grid can simply be a map of coordinates, and that allows us to have negative coordinates and prevents us from needing to redefine the bounds of a 2D array. For this problem, I'm going to use complex numbers. You'll see in a bit why that makes things easier. We used this concept in a previous problem, but long story short, the complex numbers live on a number plane rather than a number line. We have the real number line along usually what's represented as the horizontal axis for visualization purposes. And then we have the positive imaginary and negative imaginary direction. We can define a coordinate. For example, if this is the coordinate 4, 3, we can define that as the real coordinate, or the x direction, plus the y direction times the imaginary unit of I. So that allows us to define a coordinate as a complex number, which has two benefits. First, it lets us add it to another offset. So for example, if we want to increase this by 2 and this by 3, we can just add 2 plus 3i. It also lets us take the difference, which is basically the same thing, we just do subtraction instead. And finally, it allows us to rotate values by 90 degrees very easily. multiplying by I will rotate your number around the origin counterclockwise by 90 degrees. I'm not going to go into a full explanation of why, but it essentially has to do with the way that I times I is equal to -1 by definition. Okay, so we'll set our grid, which will begin with our starting position of 0 equal to the character s. Then, for each turn, direction, and wall size in our instructions, we'll add that section to the grid. So we start facing upwards, which we have chosen to represent it as 1j. Let's call that d to avoid confusing it with the built-in function for directory. And we will keep track of our current position, which starts at 0. Okay. So first we perform the turn. So if we're turning to the right, then recall earlier that I said that multiplying by I will rotate counterclockwise by 90 degrees. So to multiply clockwise by 90 degrees, we multiply by -I. And the reason for that is because multiplying by -1 flips it over the origin. So if we want to rotate clockwise 90 degrees, that's the same thing as rotating negative and then flipping. So if we're turning to the right, then we multiply the direction by -I. Also, as a reminder, in Python, J is the symbol used to denote the imaginary unit. I believe that's a thing from engineering. I think they use J as their imaginary unit over there. But I come from math, so I'm more familiar with calling it I. Otherwise, if the turn is to the left, we multiply it by +I. And then we start a loop in the range of the size of the wall. Each time we increase the current position by the direction. Here you'll see the advantage of using complex numbers. This allows us to step by the direction offset very easily. And then we'll set the grid at that position to a wall. Finally, we'll set the last known value to the end state. So if we print out our grid, we'll get a map from coordinates to cells. And so this isn't very nice for visualization. I won't bother representing the visualization, but you can do a sanity check and see that the end position is marked at -6, -6, which should tell us it is 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6 cells left and down of S, which it appears to be. So now let's do the breadth first search part. We're going to use the built-in deck class as our queue once again. So we'll keep track of a scene set, which starts with the initial value 0, and a queue, which starts with the initial scene set. And in this case, since we do care about the distance and not just whether or not we can find it, we'll need to store the distance in our deck. So we'll make our deck a list of pairs. The first value in the pair is the distance to the node, and the second value is the coordinate that it's at. So while the queue is not empty, we'll get the distance traveled and the current coordinates by hopping from the start of the queue. And then we'll look at all of the neighbors. So for neighbor in current -1, that's the value to the left. Current +1 is the coordinate to the right. That's the value below. And that's the value above. We'll check a couple of things. So first of all, although it probably won't matter in a grid of this size if the start and end positions are somewhat confined like they are here, if the map is a bit more open, we don't want to just run off the edge of the grid forever. So let's find the bounds of the map so we can somewhat intelligently clamp it. We don't want to avoid going outside of the map at all, because it's possible that we have to in order to get around the walls. So we will give ourselves a tolerance of one cell, but there's no reason to go more than one cell past the edge of the grid. So the topmost position is going to be the imaginary coordinate or the imaginary component that is maximal across all coordinates in the grid. And since the coordinates are stored as the key, that means we can do max for x in grid.keys. And since iterating through a grid by default just goes through its keys anyway, we can just do for x in grid. We will maximize the imaginary value, and then we'll add 1 as a bit of tolerance to allow us to go around walls in case it's necessary. Same for the bottom. And then the left and right will use the real coordinates, like so. Okay, so if this value is in bounds, so b less than or equal to n less than or equal to t, b less than or equal to n's imaginary component less than or equal to t, and the real component is within the bounds of L to R, and we have not yet seen it, and the value there is not a wall, then a couple of things. Firstly, if we find the end position, then we can just exit here. So we'll print out the distance traveled plus 1 because there's one extra step needed to get to the end cell, and then we will exit the program. If that's not the case, then we'll add it to the scene set, and then we'll add it to the queue. We'll increase the distance traveled by 1, and this should give us our answer for parts 1. Sorry, the answer is printed here. Okay, so that works for the sample input, and testing it on our real input, we get our answer. Part 2 is exactly the same thing. The only difference is the size of the input, but because this is a fairly sensible approach for grids of a size that can be searched within reason, that just solves the problem. I think if we remove these constraints, then the problem approach probably will take too long. So I think this approach maybe is the intended difference between part 1 and part 2. Or it is also possible that there's just no difference between part 1 and part 2, and you're supposed to be able to just run the same code again. Part 3 is, once again, still the same problem, but you can see from the input sizes that these values are no longer within reason to search the entire grid. We're going to need some optimization to skip through some steps, and in this case, the shortcutting comes with being able to travel more than one cell at a time. So let's suppose we have some start position, some end position like so. Now we'll observe that there's no point in traveling to any cells in the middle like this, because really what we can observe is that the only time we ever need to make a turn when we're traveling is if there's a point of interest somewhere on the grid. And what I mean by that is there is a vertical wall at that column, or there's a horizontal row, or there's a horizontal wall at that row, or the start or end position is at that, or sorry, not even the start one, just the end one is at that row or column. So as an example of what I mean, if we pathfind this way, one thing we can observe is that once we go up here, we go to the right, and there's no reason ever to turn. So we don't need to compute each of these cells individually. We can simply skip ahead to the next point of interest, which is here, and then we can just do something like that. So we don't actually need to check cells where there are no points of interest. This allows us to fast forward and jump past the vast amounts of gaps, because we note that we're only drawing a total of We're drawing a total of 240 walls on a massive grid. That means that most of this grid will consist of empty space and just a long wall stretching off for millions of units. So we need to be able to shortcut this by only stopping whenever there's something of note. Now we can't just stop at walls because we could also have a situation where, for example, we approach from this side, and then we need to be able to stop at this position. So basically, each time we pick a direction, we'll look for all points of interest in perpendicular to that direction and add all of those to our queue. The way I found that makes this work is each time we have a vertical wall, we'll add it, the column to its left, and the column to its right to the list of POIs. And each time we have a horizontal row, we'll add it, the row above it, and the row below it to the list of POIs. This basically allows us to find the position where we can turn after we've passed a wall. Now you could optimize this even further because we are going to still make a couple of nonsensical turns, but I find that it's generally not really worth it to optimize any further than this. One thing I will, however, note is that we're no longer adding items to the queue in increasing order of distance. The purpose of breadth first search, or rather, one of the things that makes breadth first search work, is each time we add something to the queue, it is strictly or it is greater than or equal to all of the elements before it in the queue in terms of its traveled distance. Basically, we start with a value, an item of distance 0, and then we pop it, and everything we add will have distance 1. Each time we process one, we'll append one or more things with distance 2. And so the queue always is increasing. And this means that the first time we find a cell is the optimal way we find the cell. This is not the case when we're no longer searching with a distance increase of 1 each time. Now we're searching on what's known as a weighted graph, which means that we can have situations like this, where if we just took the first method found, we would do something like this. We'd add this to the queue, and then this edge is lower, so we'll add it first, and then we'll add this one second, and then we'll process this one next and see this item. If we stopped here, we would just say, okay, this has distance 51, which is clearly wrong because there's a more optimal path if we take the less optimal first initial edge. The way we do this is we want to keep track of the total accumulated distance and each time process the node slash path pair that has the lowest traveled distance. So let me demonstrate an example and then discuss how we're going to implement this. So first we add this to the queue with distance 1, and then we add this to the queue with distance 2. Now we're still going to process this one first, and then we'll add this one to the queue with distance 51. But before we do anything here or acknowledge this as complete, we're going to go back and process the next lowest item in the queue, which is going to be this one with total travel distance 2. We'll process that one, and then when we get here, we'll add this to the queue again, but this time with distance 5. So then when we go to process this, we'll see, okay, we processed this with distance 5, which means that the optimal distance is 5. Basically, we only end when we actually go to process a node and not when we add it into the queue. Now in this example, we didn't actually change the order in any case, but there are situations in which items inserted into the queue will be smaller than items that were inserted before. This means that we can't just use a queue, we have to have some sort of queue where we can insert items in any order and pull them out in a sorted order. Now, how can we do this? This is exactly what the priority queue data structure is for. The abstract data type of a priority queue has two operations. It allows us to push a value, which will insert it into the priority queue, and it allows us to pop, which will return us the lowest value in the priority queue. So for example, a naive implementation of this would be whenever we push, we just .append to a list, and then we call .sort. and then whenever we pop, we just pop the first element. This would work, but it would be incredibly inefficient because each time we add a value, we have to sort, which is an inefficient algorithm. I'm not going to go into specifics of how time complexity works, but for those who are familiar, it's O of n log n. Basically, this is a bit worse than linear, but it's pretty close to linear for most applications. But doing a linear time operation every time we insert is still going to be incredibly slow. What we're going to use is something called a heap. A heap is an implementation of the abstract data type that represents a priority queue. I'm not going to go into too much detail here. I'm just going to go into a rough explanation of how heaps work, mostly just because it's relevant and it's kind of interesting. But you don't really need to know how it works behind the scenes if you just know how the Python library works. But I'm not a huge fan of just throwing libraries at things if you don't understand them. Not because I think that's like cheating or anything, but just because I think there's value in learning how things work. So I'm a bit rusty, so forgive me if this explanation doesn't go perfectly. But essentially, we have a structure which is a binary tree, meaning it's a tree with some root where each node has 2 or 1 or 0 children. It's called binary because the number of children is 2. Basically, it branches off in twos at a time. The rules for a heap are very simple. Each child is larger than its parent. That might seem counterintuitive, but you can also do it the other way around with each parent being larger than its child. That's what we call a max heap. This is what we call a min heap because the minimum item is on top. You'll notice that not every item will be larger than each item in a layer above it. This 3, which is the grandchild of the root, is smaller than the 5, which is the parent, or sorry, the child of the root, but that's fine. The only thing we care about is the relationship between a parent and its direct children. Each child must be larger than its parent. So let's say we want to insert 4 into this heap. Well, what we can do here is add it to the very bottom of the tree in the last available position. Or rather, the first available position? I don't quite remember. And then we heapify, which means we repeatedly take this item and put it where it needs to be. In this case, nothing needs to change. Let's do a somewhat more interesting example. And let's say we want to insert 2 into this heap. So let's say we put it here. It's not arbitrary where we put it. I just kind of forget how exactly this works. I'm pretty sure this is not strictly valid because I think your heap needs to be left aligned, but I'm a bit rusty on data structures. We then take 2 and compare it to its parent. We see that 2 is smaller than its parent, which is illegal. So we take a look at its parent and its 2 children. In this case, it doesn't have 2 children, so we just swap the 2. We'll see where things get interesting right here. So now we again look at 2 versus 5. And we see that 2 is still smaller than 5, which is an illegal relationship. So we need to put the 2 up. However, we could also have a situation where, let's say we're inserting a 6 here, and there's a 5 here and a 4 here. Or sorry, that would be a legal relationship. Let's say we have something like... No, I'm still having trouble finding. Hold on. Yeah, let's say we have something like... I'm completely forgetting what the issue is with just making the swap, but I recall there is a case where if we just swap these 2 items, then it creates an illegal relationship between these 2 items. I'm kind of struggling to remember how that can happen. Because this is already illegal. Never mind. But basically what we'll do is we'll look at the illegal parent and both of its children, and we'll promote the smallest one to the parent and move the parent down to where the child is. So in this case, that'll be like so. Um, but it's yeah, I guess it's never possible that this one is the minimum. I don't know. I'm kind of confusing myself here. Either way, we repeat this heapify operation until we're done, and now we have once again a valid min heap. To pop a value, we'll pop a value off the top. So basically, sorry, before I continue, the reason this algorithm works so well is that when we insert an item, the number of swaps we need to make is at most equal to the height of the tree. And because it's a binary tree, each time we add a layer, we effectively double the capacity of the tree. And the inverse relationship to exponentiation is the logarithm. So what this means is that inserting an item takes time proportional to the logarithm of the size of the tree, and this is comparatively fast. This is pretty much instant for because log n is grows pretty slowly. To pop the smallest item off the heap, we simply take the first item out. Now, when we take the first item, we can't just remove it because now we no longer have a valid structure. So what we'll instead do is we'll swap it with the last item, and then we'll delete it and return its value. Once we've done that, we now once again have an illegal relationship here. Ah, I think, yes, this is where things now make sense. Okay, so I was wrong. When we heap push, we can just swap items. When we heap pop, we have to see which item to swap with. Okay, so let's suppose we have this situation here. Um, we have to make sure we swap this with the smaller of the two children, because if we swap this with the 4, then this relationship here would still be invalid. Okay, so basically, each time we look at the parent, if it's larger than one of its two children, we will swap it with its smaller child, and then we'll look at it again and repeat, and we once again have a valid min heap. Fortunately, you don't really need to know how any of this works under the hood because most languages already have this implemented. Python has this implemented in the heapq module. The heapq API essentially has the following functions. We can heapify a list, which takes a list and sorts it according to the heap algorithm. Um, it, it actually, the way the heap is represented, you can actually just sort a list. And then the actual object that this heap queue is stored in is a list. As long as you don't do anything to the list besides heap push and heap pop, you'll be fine. So then let's suppose we have a queue that initially begins empty. We can do heap queue dot heap push pq and some value. And then we can do heap queue dot heap pop, and it will give us the smallest value each time. Um, I hope I have heap queue imported or installed, I mean. Yeah, okay. Heapq does seem to be a standard library function. I don't know why I'm not getting my autocomplete here. So this is going to be the implementation for priority queues. So this explanation of how priority queues work and the heap implementation of it is mostly just a fun exercise for the purpose of education. You don't need to implement this yourself. You can just use heapq. Okay. So let's get on with the implementation. So first, we're going to still take the instructions, but now we're not going to store a grid anymore because it would be completely impractical to do so. Instead, we're going to store a list of walls, and the way I chose to store this was a list of triples. The first value is the direction that the wall faces. The second value is, I guess, I did that during the contest, but let's make this a class so we can be a bit more. This can make a bit more sense. So we'll define a wall as a value containing three attributes. Whether or not it's horizontal, which will be a Boolean value that's either true for horizontal or false for vertical. A start position, which will be a coordinate as a complex number once again, and an end coordinate. And these will define the bounds of the wall. So now walls can be a list of objects of type wall. So once again, copying some of this over, instead of doing a loop over the size, we'll just add a wall. So walls dot end, we'll create a new wall object. So the self here is an object that's passed into the double underscore init function that serves as the constructor for the class. We don't need to pass it in ourselves. When we call the constructor for a class, Python automatically instantiates an object and then passes it to this function automatically. So we just need to provide the horizontal start and end options. So it's horizontal if the direction is real, so 1 or -1. So if direction is 1 or -1, then it's horizontal. The start position will be P plus D because the wall starts one step in the direction that we have turned towards. And then the end is P plus D times size. And then we'll set P equal, or we'll increase P by D times size, like so. And now one thing we do want to do is because we're trying to reach the last point on the wall, that means that we want to basically remove that segment from the wall. So basically, we want to just chop off the last cell of the last wall. And so the way I'm going to do that is keep track of an index. And then we'll know we're on the last wall if the index is equal to or the length of the instructions list -1. So if that's the case, we will subtract 1 from the endpoint, or rather subtract D. So um, say end equals P plus D times size. If this is the case, then we'll subtract 1 from the size, basically. Okay. So because the problems are the same across all three parts, we can go back to the start and use our old test cases. This means that we can visualize the code a lot more easily. So let's print out the walls. I guess I need to define a guess I need to define a way for it to be printed out so that we can actually see it. Okay, so we see that there's a horizontal wall from -1 to -6. That's this section here. Then a vertical wall from -6 minus 1i to -6 minus 3i, which is these three blocks here. Then from -5 minus 3i to just 3i, which is here, going back to the column or the real value of 0, and so on and so forth. Now let's track those POIs I mentioned earlier, points of interest. So the real POIs will represent the vertical walls, and the imaginary POIs will represent the horizontal walls. Okay. So if D was in 1, -1, then that means that the wall is horizontal, which means that the POIs are going to be in the imaginary axis because we're trying to stop at that given row. And so to POI imaginaries, we will union in the set of that row, which is going to be p dot image, and that minus 1 and plus 1. So this will mark the row containing the wall and the row above and below it as POIs. I don't actually know if you need to mark the row itself as a POI, but just to be safe, I'm going to include it anyway. And if that's not the case, then we want to mark the columns as POIs in the real axis, like so. So let's sanity check the POI reals. We see that we have 1 at 0, which makes sense because of this wall. 1 is here because it's to the right of the wall. 2 is here because it's to the left of this wall. 3 is here. 4, 5, 6, and finally, I'm not sure why 7 is here. And then negative 13 will be the value here. Okay. So that'll give us the POIs for the rows and the columns. Okay. So let's see where we were. Now we can move on to the actual pathfinding itself. I guess we still do want to mark down what position is the end position. So end is going to be the end position that we're trying to get to is going to be the final position that we tracked. So it still should be -6, -6. Okay. So let's get started on the pathfinding. Also, as a side note, the search algorithm I mentioned earlier, this one, where you use a priority queue to keep track of all of your states, and each time you get the state with the lowest total distance from the start position, is known as Dijkstra's algorithm. I have no idea how to pronounce that properly, but yeah, that's how you spell it. Breadth first search is actually basically a special case of Dijkstra's. If all of the edges have weight 1, then then in place of a priority queue, you can simply use a queue. And the optimization to stop when you see a node instead of when you process a node just saves you 1 layer of breadth. So, or 1 layer of depth, I guess. So BFS is a sort of a special case of Dijkstra's algorithm. Okay, so we'll start with our. We still do keep track of a scene set for Dijkstra's algorithm, but we only mark a node as scene once we've processed it. Once we've processed it, we know we have already found the fastest way to get there. So any future edges that go to that node are, what's it called? Are suboptimal, so we can skip them. So rather than adding to the scene set when we add a node to the queue like we did in BFS, we'll add it when we process it. That also means that initially the scene set starts empty and doesn't even include the starting position. The priority queue will start including the position, and we're going to store 3 values in the priority queue. We're going to store the total distance, and then we're also going to store some arbitrary increment. And the reason I'm storing this increment is because complex numbers cannot be compared. Complex numbers are not totally ordered, which means that you can't use less than greater than to compare them. So if you put them into a priority queue, like if we just put something like this into a priority queue, then if we later got another value with the same total distance, because Python sorts lexicographically, it would first compare the first position in each value, and if they are equal, then it will compare the second value. And because those are both complex numbers, that'll actually crash the program. So the hack I use to work around that, there are technically better ways to do it, but I'm a bit lazy. The hack was I just kept a unique incrementer, and because it's arbitrary which value we visit next, whenever we, because it's arbitrary which value we visit next when we pull from the priority queue if there are multiple nodes with the same total distance, that means that we can just insert some arbitrary value to prevent duplication. So the second item in each triple is just going to be a unique value whose only purpose is to be unique. We won't process it at all. We're just using it to avoid duplication. Okay. So the first item will get an increment value of 0. And then that's what our priority queue is going to start out as. Total distance from the origin is 0, arbitrary increment value is 0, and we're starting at the actual coordinate 0. So while the priority queue is non-empty, we will use heap queue.heap_top to get the smallest value out of it. So that's going to be the value with the lowest total travel distance, and failing that, the value with the lowest arbitrary increment. So the first value is going to be the distance, the second value is arbitrary, so we'll skip it, and the third value is our current position. From here, if the current value has already been seen, we'll just skip it. Otherwise, we'll now add it to the scene set. And also, if it is the end position that we're searching for, we're going to print out the distance traveled and exit. Okay. Now we can look through all of the neighbors. For n, I guess we're not looking at neighbors anymore, we're looking at directions that we can travel in. So for B in, we can go right, left, up, or down. For each of those directions, we'll first want to figure out how far we can travel before we hit a wall. So this code is going to be a bit tedious to write out, so forgive me for the length of this video. Okay. So we're moving horizontally if d is equal to 1 or negative 1. And we're going to want to see what the furthest we can travel is. So farthest equals initially infinity. And okay. So for each wall, there are two possibilities. If they're both horizontal, if the wall is horizontal and we're currently traveling horizontally, then if the wall is in our way, the farthest we can travel is up to the leftmost point of that wall minus 1. And so if we're moving horizontally and the wall is also horizontal, then we'll check something. So if the direction we're moving is positive, then if the wall's start value, if the wall start value's real position, which is the column that it resides in, is greater than, sorry, we should be using min here. Basically, we can't be inside the wall. We're just going to assume that we're not inside the wall because we should never be able to get into that position. So we're either to the left of the wall or we're to the right of the wall. If we're to the right of the wall, we don't care. So if the leftmost point, which is the minimum of the start and end position, is greater than our current position, which is not real, then that means the wall is to our right. And so we'll clamp farthest by the distance to the wall, which is going to be the aforementioned minimum, which is going to be the aforementioned minimum minus our current position, and then minus another 1 because we can't actually end up inside the last cell of the wall. We need to end up 1 to the left of it. Otherwise, if we're moving to the left, then we care about the rightmost position of the wall. And so if that point is to our left, then we'll clamp the farthest by the distance to that, which is going to be this time our current position minus pt because they're the other way around, and then minus 1 again. if we are moving vertically and the wall is also vertical, then we're basically just going to repeat this entire thing, but imaginary instead. So if we're moving up, then we're going to look for the minimum imaginary coordinate. And if we're moving down, we're going to look for the maximum imaginary coordinate. I'm sure there's a way you could write this better to avoid this code duplication, but for contest, solving this kind of approach is, I think, reasonably acceptable. It's not like you're going to go back to this code and need to maintain it in the future. Finally, not finally, if we are moving horizontal and the wall is vertical, then and I'm sure there's a way you could combine these cases as well. I think I'm just being a bit lazy with the logic here. Um, if we're moving horizontally and the wall is vertical, then we need to make sure that we're between the top and bottom positions of the wall. Oh shoot, something I forgot to check here. We only care about horizontal walls if we're in line with them. So I guess this means that if the wall's row is different from our current row, then we don't care about the wall. Oh, that actually makes me realize that there does seem to be a way to simplify this logic a lot. Okay. If we're traveling horizontally, then we only care about the wall if we're between the start and end of the wall, vertically speaking. So basically, that means that the minimum, which is the bottommost row that the wall occupies, should be less than or equal to our current row. So if that's not the case, if we're currently below the bottommost row that wall occupies, we skip it. Likewise, if we're above the uppermost row it occupies, we skip it. This just becomes duplicate if the wall is horizontal, then this check still works. These two values will be the same, and this check will basically just assert that they're equal. Okay, this makes more sense now. And then this works just fine for both vertical and horizontal walls, because if the wall is vertical, then this value is just going to be the same because these two will be equal. Okay, this makes more sense to me now. So I think this allows us to avoid heavy amounts of code duplication. Okay, and in this case, we do the same thing, but we just flip the real and imaginary values. Okay, so now if we're moving vertically, then we want the walls to occupy the column that the current value is in. And if it does, we'll look for the walls, the row that the wall's in to see where we'll hit it. Okay. So at the end of this, this should give us the farthest we can move. If we just output that and do nothing, did I forget to import heap cube? We get this. So let's sanity check that. We're starting here. It's saying we can move 2 positions up, or sorry, to the right, which appears to be the case. We can move 2 spaces to the right before we hit a wall. It's telling us we can move 0 to the left, which again checks out. We can move 2 up, which is the case, 1, 2, and then we'll hit the wall. And it's saying we can move 2 down, which again is the case, 1, 2, and then we'll hit a wall. So it looks like this logic is working so far. So now we just need to make these actual moves. So because we stop when we reach a wall, then that means that the farthest we could move to is either going to be infinity if there's no wall at all in that direction, or it's going to reside at a POI. So we want to check all POIs that are in the direction we're moving in and are closer than the farthest point we could move. Basically, before we hit a wall, but we want to stop at any POI in case we want to turn there. Also, I did forget to add one more thing. we do want to add the end position to the POIs. Um, I It does sort of matter because if we do something like this, then the row that the end is in would already be a POI because of this edge, but the column wouldn't be unless we directly add it. And since we're using a set, it doesn't matter if we add duplicate values because they'll just be removed anyway. Okay. So now that we have the farthest distance we can travel, we want to look for all POIs in that direction that are closer, that are within range, basically. So if we're moving horizontally, then for each POI in the column-wise POI, so as we're moving horizontally, we want to stop for any vertical POIs, which will be in the real list. If the POI is in the wrong direction, so if we're moving to the right and the POI is to our left, or moving to the left and the POI is to our right. And I guess we also want to skip any POIs that are currently on top of us because we obviously don't want to make a movement of length 0. Then we'll skip it. Additionally, if the difference between the POI and our current position is greater than the distance we can travel, then we'll skip it. Otherwise, we'll add that to the priority queue of places we can visit. So heap q dot heap push, pq, and our triple. So the step size we're taking is going to be added to the distance that we've already traveled from the origin so far. So dist plus step. We'll set the increment to the next available value. So increment equals increment plus 1. And finally, we will insert the coordinate that we end up in. So the coordinate we end up in is going to be the real value we travel to, which is the POI, plus the imaginary value we travel to, which is cur.imag times 1j, like so. Basically, we're reconstructing a coordinate where the real coordinate, or the horizontal axis coordinate, is the POI that we've stopped at, and the column coordinate is just going to be where we already were because we're traveling horizontally. And then the rest of this will be pretty much similar, but we're now replacing real with imaginary, and the imaginary part with the real part. So now we're reconstructing where the real coordinate is our current real coordinate and the imaginary coordinate is the POI. Okay. So to be clear, I have no faith that this will work, but that's that's par for the course for these contest problems. You're hardly ever going to get it right the first try with these more difficult problems, and so that's what trial and error is for. Okay, so we get an answer of 12, and that's clearly wrong. So let's see what we messed up here. Okay. That's not very helpful, is it? I forgot to skip the C in valleys. Yeah. Okay, once we've seen a valley, we also don't want to add it again. So if no, I guess we print this after we skip scene items. Okay, that's a bit more helpful. All right, let's see. So we start at 0, 0. We can move to this position in one step. We can move here in one step, which appears to be what we want to do. 1j. Okay. There's a lot of values to scroll through. I don't think this is actually going to be very much help. Um, I guess one thing we can do is add a list of steps we've taken to get to this point. Um, Not always a huge fan of this approach, but it does work. Let's call it path. Um, okay. So each time we take a step, when we do the heap push operation, we're just going to take path and add how we got here. So the way we got to this position, we'll just add cur to the path. So that'll basically let us backtrack how we got to our final point. Okay. So it tells us we are from 0 to minus 2j to minus 6j. So it's saying we went straight through this wall. All right then. Well, how does that one work? So the problem's being observed at negative 2j. So I guess we should insert a print statement here. If we're currently at negative 2j, let's print out the wall each time we encounter a wall. And then at the end, if cur is equal to negative 2j, we'll print out the farthest. I guess we don't need to do that. Okay, so moving up, it tells us we can go as far as say we can go as far as 2, which is sorry, to the right we can go as far as 2. Up we can go as far as 5, which 1, 2, 3, 4. That's not right. Should only be able to go up 4. Sorry, that's to the left. To the left we can go 1, 2, 3, 4, 5. Yeah, that checks out. Up we can go 4, and down we can go 0. So it is correctly telling us that we cannot go any further down, and the maximum distance going down is 0. And if it's negative 2j and we're moving vertically, we'll print out the POI that we're going to, step, and the farthest. Okay. So while we're moving down, we get a POI of negative 2 and a step size of 0. I mean, I guess, but I did explicitly say that we're not allowed to. Oh, I see. Yeah, I just made a copy-paste issue. I forgot to change the comparisons for the directions. Let's see if that fixes the problem. Yeah, that actually seems to solve it. Cool. So just a very silly copy-paste mistake on my part. But it looks like we might have ourselves a solution for part 3. Let me just remove the path because that will get very laggy because we're storing a lot of data in PQ and XS right now. So let's get rid of that. I don't like how long that takes, but it seems like it's getting us the correct answer. Yeah, for some of the smaller grids, this approach might actually be slower than the main approach because if the grid is pretty densely compacted, then we're going to end up visiting basically every square anyway. And so I suppose this ends up being problematic because we end up using each step takes longer than in the BFS approach. I guess one optimization we can add is don't add items that are already seen. So if we've already processed an item, then we don't need to add it anymore. So if and in scene continue, I think doing this might improve performance a bit, but I'm honestly not sure. Okay, I don't know if that actually improved performance, but it's still not a bad change to have. And let's try this with our actual input. I'll fast forward a bit so you don't have to sit here and wait with me. And after a somewhat stressful wait of almost a minute and a half, we do fortunately get a right answer for part 3. So performance definitely leaves a lot to be desired, and again, if you know of a more efficient solution than this, please do share, as I'm always interested in finding optimizations. Um, but given that the fastest human solution for this took 50 minutes, this runtime is not really a concern. So definitely on the longer side as far as videos go. I'm hoping that not all of these will be like this because I'm not sure I'll have the time for that next week. But thank you very much for watching. I hope you learned something in this video, and have a good weekend. I'll see you again on Monday for day 16.